This video is going to cover the special relativity topic for special higher physics. You should use this video in conjunction with the typed lecture notes that can be downloaded from Moodle. Prior to the 20th century, things generally didn't move too quickly. So at this time, there was transformations called the Galilean transformations that were accepted as the transformation of how you get from one reference frame to another. Let's have a look at the Galilean transformations. Imagine that we have Joe here in reference frame S. A point P in this reference frame is given by x, y, z, has x coordinate, a y coordinate and a z coordinate. Now imagine that Mo is moving relative to Joe. This is Mo's reference frame. It's called reference frame S prime, and it is moving along the x-axis of Joe's reference frame with a speed u. So point P in Mo's reference frame has coordinates x dash, y dash, and z dash. And let's have a look at the relationship between x and x dash, y and y dash, z and z dash. Well, x dash is equal to Joe's x coordinate, and now we need to subtract off this ut term, as this distance you can see is shorter than the x distance in Joe's reference frame. Now in the y direction and the z direction, there is no relative movement between these two frames, so these coordinates stay the same. So we've got y dash is equal to y and z dash is equal to z. And obviously time is not going to depend on your reference frame, so we also have t dash is equal to t. And these are called the Galilean transformations. Now, up until the beginning of the 20th century, it was thought that these were good transformations, as it was commonly believed that the laws of physics are the same in any inertial reference frame. An inertial reference frame is one which is undergoing constant velocity, it's not accelerating. And so most of the laws of physics, if they apply in Joe's reference frame, also apply in Mo's reference frame. Let's just have a quick look at a common law of physics, Newton's second law. Okay, let's assume that it holds in Joe's reference frame. So we know that if we apply a total force, then we'll get an acceleration m d squared x dt squared. And let's have a look at what's going to happen in Mo's reference frame. So we have, we can write this first transformation up here as x is equal to x dash plus ut. So this tells us that dx dt is equal to dx dash dt plus u, and so we've got d squared x dt squared is equal to d squared x dash dt squared, and then using the fact that t dash and t are identical, we've got d squared x dash over dt dash squared. So we can write this as m d squared x dash over d t dash squared is equal to f total dash, i.e. if Joe feels a force in his reference frame, then Mo feels the same force in his reference frame. However, at the beginning of the 20th century, some problems were starting to emerge with this picture, in particular with the speed of light. Maxwell had just come up with some equations, and Maxwell's equations actually predicted that the speed of light should be the same in all reference frames. Now, if we use the Galilean transformations, that's just not true. Let's assume that light has speed c, which is equal to the displacement over the time in s. Then in S dash, we've got that the speed is x dash over t dash. Now x dash is equal to x minus ut, and this is over t dash, which is the same as t, so this is equal to x over t minus u, and x over t is equal to c, so this is c minus u. So you can see that if light is travelling with a speed c in frame S, in Joe's frame, it has a speed c minus u in Mo's frame. And this was an issue because it means that you can conduct experiments with light and you can then work out which reference frame you're in, how fast your reference frame is going. So the laws of physics are not all the same in all reference frames if these Galilean transformations are true. Now, at about the same time, Lorentz came up with some transformations which allow for this constant speed of light. So the Lorentz transformations can be written as x dash is equal to x minus ut over the square root of 1 minus u squared on c squared, which is sometimes written as gamma x minus ut, where gamma is equal to 1 over the square root of 1 minus u squared on c squared. Y is equal to y dash, z is equal to z dash, and the interesting one is the time. T dash is equal to t minus ux over c squared over the square root of 1 minus u squared on c squared, which is equal to gamma t minus ux on c squared. Now we can show that if light has a speed c is equal to x over t in Joe's reference frame, then using these transformations, the speed of light in Mo's reference frame is x dash over t dash, which is equal to gamma x minus ut over gamma t minus ux on c squared. These gammas will cancel out. Let's divide both the top and the bottom by t. So we've got x over t minus u over 1 minus u x on t over c squared. Now x on t we've said was c, so this is c minus u over 1 minus u on c squared times c. So this is equal to c outside of 1 minus u on c over, this cancels, 1 minus u on c, this part cancels, so this is c. So if something is travelling with a speed c in Joe's reference frame, it is also travelling with the speed c in Mo's reference frame if we use these Lorentz transforms. This brings us to the question, what experimental evidence is there that these Lorentz transformations are correct? One of the first pieces of experimental evidence was the results from the Michelson-Morley experiment. The Michelson-Morley experiment was designed to measure the velocity of the Earth through the ether. At the time, it was thought that since all mechanical waves needed a medium to travel through, light waves also needed a medium to travel through. This medium was called the ether, and it was thought that the ether provided a reference frame against which the movement of all objects should be measured. Now, as the Earth goes around the Sun, here's the Sun, here's the Earth, it also spins around its axis, but it travels around the Sun, its velocity changes as it's changing direction. And so the Michelson-Morley experiment was run at different parts of the year to try and detect this changing velocity of the Earth. The apparatus set up to test the Michelson-Morley experiment involved a light source that was shone through a semi-silvered mirror. This is at B, and so this reflected some of the light up to a mirror here at C and let some of the light rays through it to another mirror over here at E. Now the distance from B to C is given by L, and the distance from B to E is also given by L. These are the same distances. Then the light reflects off these two mirrors, comes back here, some of it passes through, some of it is reflected downwards to an analyzer where the diffraction pattern is looked at. Now, if the distances between B and C and B and E are exactly equal, the path difference is the same for the light, and so it should be perfectly in phase when it arrives at the analyzer. If the path difference is changing between them, then we'll get a changing diffraction pattern in the analyzer here. So let's now assume that this apparatus is moving through the ether at a speed u, going in this direction, so along the BE axis. Well, after a time t, these mirrors have all moved onwards a bit. Let's draw their new positions. So here's C dash, here's E dash, this distance is UT, again this distance is UT, and our semi-silvered mirror has also moved along here, B dash. Now let's have a look at how long it's going to take the light to go from B to E and back to B, and then we'll have a look at how long it will take the light to go from B to C and back to B in the case where it's moving through the ether like this. Let's call the time from B to E, or E dash in this case, is equal to T1. So T1 is equal to the distance over the speed. The distance it has travelled is it's had to travel this distance L, and then it's had to travel the additional UT. So that's the total distance travelled. This is T1. And then the speed it's going at is c, as it is a light wave. And so what we want to do is just get an expression for t1. So we can write ct1 is equal to L plus ut1, and so t1 is equal to L over c minus u. Now time from E dash to, well, it'll actually be B double dash, as this B has moved onwards again to here. Let's call this T2. Now the mirror B dash is moving towards the light ray, so the total distance it has to cover isn't L, the distance between B dash and E dash, it is in fact L minus UT2 over C, as it doesn't have to travel this distance, as this is the distance travelled by the mirror in that time. And so just rearranging this, we have T2 is equal to L over C plus U. So the total time for it to go from B to E and back again is T1 plus T2, which is equal to L over C minus U plus L over C plus U, which is equal to LC plus LU plus LC minus LU over C squared minus U squared. This and this will cancel, and so we end up with 2LC over C squared minus U squared. So that's the time it'll take along this arm. Let's now consider the time it'll take along this arm. So let T3 equal time taken from B to C. Now the light has to travel along this path here to get to the mirror. As the mirror is no longer at C at time T3, it's moved along a distance UT3. And so we've got this distance is L, this distance along here is UT3, and so using Pythagoras' theorem, the distance it's travelled is the square root of L squared plus UT3 all squared. And to get the time, we divide by the speed it's going at. So we want to find out T3, so we've got T3 squared C squared is equal to L plus U squared T3 squared. So that tells us that T3 is equal to L over the square root of C squared minus U squared. Now the light needs to travel from B to C and back to B. That's the time it takes in the arm. So total time is just double the time going up. So it's equal to 2T3. So it's equal to 2L over the square root of C squared minus U squared. Now the interesting result from the experiment is that these two times are not the same. We've got 2L on C squared minus U squared, which if we wanted, we could write as 2L on C over the square root of 1 minus U squared on C squared. And we've got T1 plus T2, the other total time in the arm. We can write this as 2L on C outside of 1 minus U squared on C squared. And these are not the same. They're different because we've got a square root down here and not down here. So something's gone wrong because the result from the Michelson-Morley experiment was actually a null result. It showed that it didn't depend on the time of year. The diffraction pattern didn't change. And so what's the resolution to this problem? Well, in deriving these results, we haven't taken into account the Lorentz transformation. Let's have a look at how lengths transform under the Lorentz transformation. Okay, so just to recap our Lorentz transformations. We've got x dash is equal to gamma x minus ut, y dash is equal to y, z dash is equal to z, and t dash is equal to gamma t minus ux on c squared. Here we've got our reference frames S and S prime. We've got a stick. The stick is at rest in frame S dash. So it's in frame S, it's moving this way with a velocity u. Frame S prime is moving this way with a velocity u along the x-axis of frame S. One end of the stick has coordinates x1 in frame S and x1 prime in frame S prime, and the other end has coordinates x2 in frame S and x2 prime in frame S prime. Now, the length of the stick in the stick's reference frame, in reference frame of stick, which remember is the primed frame, as this is the frame which is travelling with the same velocity as this stick. So L0 is equal to x2 prime minus x1 prime. If the stick was at rest, this is how long we would measure the stick to be. So now that it's moving, the length is equal to x2 minus x1. So what we need to do now is use this Lorentz transformation to work out what are x2 and what are x1. So we have that the Lorentz transformation is x prime is equal to gamma x minus ut. We can rearrange this and put x is equal to x prime on gamma plus ut. And so just remembering what gamma is, this is x prime times the square root of 1 minus u squared on c squared plus ut. Okay, so let's substitute in here. We've got this is equal to x2 prime square root of 1 minus u squared on c squared plus ut minus x1, which is x1 prime square root of 1 minus u squared on c squared, and then with this negative sign, negative ut. So these actually cancel each other out, and we end up with x2 prime minus x1 prime square root of 1 minus u squared on c squared. And x2 prime minus x1 prime is the rest length. So this is L naught times the square root of 1 minus u squared on c squared. Now, as long as u is not 0, this thing in the square root is a number between 0 and 1. So you can see that the length is actually going to be shorter. So this is called length contraction. And this is what happens to lengths along the direction of relative motion of these two frames. So in our Michelson-Morley experiment, where we had BE and BC, and the frames were moving in this direction, U, length contraction will happen along BE, but not along BC. So L in BE is actually going to be L times the square root of 1 minus u squared on c squared. So this is going to affect our equation for T1 plus T2, because we had T1 plus T2 was equal to 2L on C over 1 minus u squared on c squared, but this L should actually be replaced with this. So we'll have this is equal to 2L times the square root of 1 minus u squared on c squared on c over 1 minus u squared on c squared. Now you see this will cancel with this, so we'll end up with the square root down there, which is 2L on c over the square root of 1 minus u squared on c squared, which was the same time it took to go along the arm BC. And so as it takes the same time to go along the two arms, we would not expect to get a changing diffraction pattern as the year changed, and so as the velocity through the ether changed. So this was experimental evidence that these Lorentz transformations were actually correct. And we've also now derived the formula for length contraction. Now we're going to derive the formula for time dilation. Imagine a rocket ship traveling through space with a velocity u. Space has the reference frame s, and inside the rocket ship we have the reference frame s prime. Now imagine that we had a clock. This is a special type of clock in which we shine a light beam from one side of the rocket ship to a mirror on the other side, and then time how long it takes to get back to this initial mirror. This would work with any type of clock. There's nothing special about this type of clock, but this is one way that we can measure time. Let's have a look at what will happen in the two frames. In frame S, where the rocket ship is traveling with a velocity u, we will see the light follow a path from one mirror to the other mirror, and then back down to its initial position like this. If we let the distance between the two mirrors inside the ship be L, this distance here is L, and if we say that the time for the trip is delta t, then this side of the triangle, right angle triangle, is given by u delta t over 2. Now considering ourselves in frame S dash, so inside the rocket ship, we see the light go vertically outwards and back, and so it travels a distance L in this case, or 2L, to get back. So let delta t dash equal time for trip in S dash. So this is easy to calculate. The distance it's gone is 2L, and the speed it's going at is c, so this is the time it takes. So this is one way for us to define our second inside the ship. Let's have a look at this one. We've got delta t is equal to the distance travelled by the light. This length is L squared plus u over delta t on 2 squared. So this is equal to, we've got two of them, it has to go there and back, so 2 times L squared plus U delta T over 2 all squared all over the speed of light. Now what we're trying to do is find this delta T. We've got a delta T here and here, so we can rewrite this as delta T squared C squared is equal to 4L squared plus U squared delta T squared. And so delta T squared, just rearranging this, we've got 4L squared over C squared minus U squared, which tells us that delta T is equal to 2L over the square root of C squared minus U squared, which we can write as 2L on C over the square root of 1 minus U squared on C squared. And now the reason for doing this is that this is now delta T dash. So this is equal to delta T dash over the square root of 1 minus U squared over C squared. And this term is some number between 0 and 1. So you can see that delta T is going to be bigger than delta T dash or delta T prime. So it looks from the outside like things take longer to happen in frame S dash, which is why it's called time dilation. Now, experimental evidence that time dilation happens comes from muons. Muons are leptons that are created in the upper atmosphere when cosmic rays travelling from the sun hit the atmosphere. The lifetime of a muon, the average lifetime, is given by 2.2 microseconds. Now, if muons were to travel at the speed of light, there is no way that they could travel enough distance to reach the surface of the Earth from the upper atmosphere within their lifetime. So the solution to this problem is actually time dilation. Within the muon's reference frame, it has a lifetime of, on average, 2.2 microseconds. But within our frame, that is dilated by this factor here, increasing the lifetime of the muon and giving it time to reach us on the surface of the Earth. Within the muon's frame, it can reach the surface of the Earth because the length between the upper atmosphere and the surface of the Earth is actually contracted, so it can actually travel a further distance than it would otherwise be able to. Now we're going to have a look at space-time diagrams. Space-time diagrams are typically drawn with a space component, usually x, along the horizontal axis and a time component along the vertical axis. Now the time component is multiplied by c so that these have the same units. This is useful because now if we have a point P here, if we want to draw light rays coming out from point P, they travel at c, and so they're going to have a gradient of 1 on this diagram. So these show light rays coming out from P. So this is actually referred to as the light cone of P. Now, light cones are important because they tell us if two events can affect each other. An event is a point on the space-time diagram. So let's say we had an event here. So here's our event. Now, there is time for light to travel from P to this event. So we can say P and this event are causally related. It's possible for P to cause this event. Now, let's imagine some other event outside the light cone of P. Now, there is no way for light or any other signal to travel from P to this other event. There just isn't time because nothing can go faster than the speed of light. So P and this other event are not causally related. Other things that you'll see represented on space-time diagrams are world lines. So here is a world line of a particle at rest. So it's always at the same x position, and the world line shows what happens to it with time. These can move about, but the gradient can never be less than 1 because we can't have anything travelling faster than the speed of light. Now let's have a look at how we would draw the axes for a primed frame S dash travelling with velocity u on these axes for P, which are drawn in the frame S. So this is in S, and we want to draw our axes in S dash. Well, in S dash, the axes will be when x dash is equal to 0, because the axes are always when x is 0. And so this we know from our Lorentz transforms that x prime is equal to gamma x minus ut. And so we've got x prime is equal to gamma x minus ut, which tells us that x minus ut is equal to 0. So x equals ut, which, because we want to get it as a line on a x versus ct plot, we will write as u over c times ct. These c's cancel out and give us back our ut, but this ct now corresponds to this y-axis here. Now our other axis will be the t prime, well, ct prime axis. So we've got ct prime is equal to 0. So this is equal to c gamma times, from our Lorentz transformation for time, we know t prime is equal to gamma t minus ux on c squared. And so this is gamma t minus ux on c squared. And so this is solved when t is equal to ux over c squared. Let's rearrange this in terms of x. So x is equal to, we can write this as c over u times ct. So you can see there's the c squared term there. There's our u. And so this is in terms of ct, or our y-axis. So we have something travelling at the speed of light with a gradient 1 there. You can see that these two gradients are the inverse of each other. So for our S dash frame, here's our x dash axis, and here's our ct prime axes. And as these gradients are the inverse of each other, we know that this angle is the same as this angle up here. So that is how we would represent the axes for S dash within the space-time diagram of the frame S. Now what we can do is use this space-time diagram to consider simultaneous events. Simultaneous events are events that happen at the same time. So for an event to be simultaneous in S, it will have to happen at a constant time in S. So any events that happen along this line here all happen at the same time, and so would be called simultaneous. Now the interesting thing is that if we want to use red now to represent simultaneous events in our primed frame, they will all be at the same t dash time, and so they will be along lines looking like this. So the red are simultaneous events in the t prime frame. They're parallel to this x prime axis here. So what this is actually showing us is that events which are simultaneous in the S frame are not simultaneous in the frame of S dash, which is very interesting. We're going to consider an example of this now. Okay, so in this example, imagine that we've got a train travelling along some tracks. Here's you standing outside the train. Now, there's a big storm on, and you see two lightning bolts hit both ends of the train at the same time. So you say these events are simultaneous. And that's in S. You're in S. Now inside the train we have the reference frame S dash. It's moving with a speed u in this direction. And here's your friend sitting right in the middle of the train. Now your friend is actually travelling towards this lightning bolt. So they actually see this lightning bolt hit first. So in S dash, let's call this A and this one B, lightning bolt A hits first. And so you do not agree that these two events happen simultaneously. Now what we're going to do is consider how the velocity of a moving particle will be transformed in special relativity. So let's look at velocity transformations. Let's just write our Lorentz transforms up here so that we remember them. X prime is equal to gamma x minus ut. Y prime is equal to y. Z prime is equal to z. And t prime is equal to gamma t minus u x on c squared. And gamma is equal to 1 over the square root of 1 minus u squared on c squared. So what we're going to be considering is two reference frames, reference frame S and reference frame S prime, moving with a velocity u along the x-axis of S. And what we'll be considering is a particle travelling with a velocity. It's got an x component and a y component to its velocity. This is point x1 or x1 prime in reference frame S dash, and this is point x2 or x2 prime in reference frame S prime. Now the velocity of the particle in the x direction in frame S is given by the distance travelled, which is x2 minus x1 over t2 minus t1, which we can write as the change in its displacement over the change in time. That is our standard expression for velocity. Now what we're going to do is work out what is Vx prime dash. What's the velocity in our reference frame S dash? So we can write that this is going to be x2 dash minus x1 dash over t2 dash minus t1 dash, which we could write as a change in x prime over the change in t prime. Now let's work out what each of these, the denominator and the numerator, are going to be. So we can write x2 prime minus x1 prime. Now using our Lorentz transform, we can write this as gamma x2 minus x1 minus u t2 minus t1. So this is equal to gamma delta x minus u delta t, and that is equal to our delta x prime, and t2 prime minus t1 prime is equal to, using this Lorentz transform over here, gamma t2 minus t1 minus u over c squared x2 minus x1. So this is equal to gamma delta t minus u over c squared delta x, which is our delta t prime. So now substituting delta x prime and delta t prime in here, we've got Vx prime, or the velocity measured in the reference frame S prime, is equal to gamma delta x minus u delta t over gamma delta t minus u over c squared delta x. Now you can see the gammas will cancel out. Now what we want to do is to get everything in terms of velocities. So we're going to divide both the numerator and the denominator by delta t. So we've got delta x over delta t minus u over 1 minus u over c squared delta x over delta t. And now what we can do is, from this top line, we know that delta x over delta t is equal to Vx. So we can simply substitute into this equation. So we've got Vx minus u over 1 minus u over c squared Vx. And so this is our equation for the transformation of the velocity in the x direction. So that's the direction parallel to the direction the frame S dash is moving in S. So let's just add this here. We've got Vx prime is equal to Vx minus u over 1 minus u over c squared Vx. Now the particle might also have some velocity in the y direction, so let's consider that. It's going from y1 up to y2, or y1 prime up to y2 prime, which actually turn out to be the same thing due to this part of the Lorentz transform here. So what we can write is Vy is equal to y2 minus y1 over t2 minus t1, which is equal to delta y over delta t. And Vy dash is equal to y2 dash minus y1 dash over t2 dash minus t1 dash, which is equal to, well, delta y, because it doesn't matter if these are primed or unprimed, and now t2 minus t1, that's delta t prime, but we've already worked out up here what delta t prime is, and this is the same length of time here, so we can substitute in this thing directly. So we've got delta y over gamma delta t minus u over c squared delta x. Now what we want to do is again get everything in terms of velocity, so we'll divide both the numerator and the denominator by delta t. So we've got delta y over delta t over gamma delta t on delta t, which is 1, minus u over c squared delta x over delta t. So you can see this will be Vy over gamma, which let's put this gamma up the top, 1 minus u squared on c squared over 1 minus u over c squared, and then this is Vx here. So there's quite a few different velocities in this equation. You need to be careful not to get confused. Vy is the velocity in frame s in the y direction. Vx is the velocity of the particle in the x direction in frame s, and u is the relative velocity between the two frames. So we've got Vy dash is equal to Vy root 1 minus u squared on c squared over 1 minus u Vx over c squared. Vz would have exactly the same form as Vy, as y and z are symmetric in these transformations. They transform in exactly the same way. Now let's just consider a couple of limiting cases. For Vx, this one, let's consider the case, first of all, where there is no movement, so where u equals 0. Well, if these frames are not moving relative to each other, then we'd expect Vx to equal Vx dash. That's what we'd expect. Let's just check. We've got, in this case, Vx dash is equal to Vx minus 0, so that's Vx over 1 minus u 0, so that's 0 times some stuff, so 1 minus 0, so that is equal to Vx, so that is correct. Let's now consider s dash moving in this direction with a speed c, so let's let u equal c. Now if we were considering a particle in frame s dash, it's going to look like it's moving at the speed of light, but in the opposite direction, in the negative x direction, so we'd expect Vx to be equal to minus c. Vx dash to be equal to minus c. So Vx dash is equal to, in this case, Vx. We can consider it to be stationary in frame S, so let's put that as 0, minus u, which is the minus c, over the square root of 1 minus, and in this case the Vx is 0, so this is 0, so this is equal to minus c, and that is what we expect. And finally, let's consider a light ray which is travelling at the velocity c in Vx, but obviously if it's a light ray it still needs to be travelling at velocity v in s prime. So this should be independent of u, independent of the relative velocities between them. So Vx prime is equal to, now Vx is c, so this is c minus u over 1 minus u over c squared times c. This c will cancel this c. So we can write this as c outside of 1 minus u on c over 1 minus u on c. These cancel and we end up with c. So that is what we expect. So we've shown that this equation at least agrees with our expectations. Now what we're going to do is have a look at momentum, because always before we've defined momentum as mv. We've seen the law of conservation of momentum. This is a very, very important rule for physics. Now, one of the postulates of special relativity is that the laws of physics are the same in all reference frames. So we expect that conservation of momentum should hold. In all inertial reference frames. So let's consider a collision. Imagine that in frame S, we have a particle here A and a particle here B. They both have the same mass m, and then travelling towards each other with speed v. Now after the collision, here's particle A, here's particle B. They're now moving away from each other in the vertical direction with speed v. Now we can see that in frame S, momentum is conserved. Initially, we've got P initial is equal to mv minus mv, and this is a vector in opposite direction, so that's 0. And P final is equal to mv minus mv in opposite directions, so this once again is equal to 0. These two are equal to the same thing. What we're going to do now is consider frame S dash. Now, frame S dash is travelling with particle B. So particle B is initially at rest in frame S dash. So U is equal to minus V. We've got particle B here with V equals 0 to start with. Here's B. And here's A. You can see that A, let's call it V1 dash, will be moving towards particle B. Now afterwards, our two particles will move off like this. We'll call the magnitude of the velocity V2 dash. You can see vertically they're going to have the same but opposite sign magnitude, and in the x component the magnitude is going to be the same. Now let's calculate the initial velocity for this case here. Now in this case, we've got that u is equal to minus v, and vx, if we look at this equation, vx here refers to the velocity of the particle in frame S. So vx is equal to v. And so vx prime, which is equal to this v1 prime, is equal to vx, which is the v, minus u, which is minus v, so that's minus v, over 1 minus u, so that's minus v on c squared times vx, which is v. So this is equal to 2v over 1 plus v squared on c squared. And so the momentum, P initial, is just equal to m v1 prime. So this is 2mv over 1 plus v squared on c squared. Now what we're going to do is calculate the final momentum. This is going to be equal to, now we've said that the vertical components are opposite and equal, so we can ignore the vertical components and just consider v2x prime along here. So here's v2 prime, and there's two of these particles, so it'll be 2m v2x prime. Now in this case, the x velocity of the particles in frame S is equal to 0. So we've got Vx is equal to, well, V2x is equal to 0. So substituting in here, we've got the 2m and then V2x dash. V2x is 0, so this is 0. Now u is the same, so this is minus v over 1 minus v on c squared times 0. So this is equal to 2mv on 1. 2mv is not the same as 2mv over 1 plus v squared on c squared. So something's gone wrong. we don't have P initial equal to P final. So we need to rethink how we've defined the momentum. So the way around this problem is to actually redefine the momentum as P is equal to mv over the square root of 1 minus v squared on c squared. Now this v is referring to the velocity of the particle, not to this u, the relative movement of the two frames, which if we wrote this as gamma, we're usually referring to the u here. So sometimes you will see this written as m gamma v, but that is a bit confusing as this gamma has a v in it, not the u. So let's not write it that way. And this v we need to transform like we do here. So let's just add this equation to our list here. We've got P is equal to mv over the square root of 1 minus v squared on c squared. And now using this, let's see if conservation of momentum holds. Now in this first reference frame there's no difference because even if we have this term it appears the same on each of these, and so we'll still have the initial velocity 0 and the final velocity is 0. The changes are going to happen over here. So let's start by calculating the initial momentum. So P initial is equal to m v 1 dash times 1 over the square root of 1 minus v1 squared over c squared. That's v1 prime squared. Now, I've just erased it, but we did show that v1 prime was equal to 2v over 1 plus v squared on c squared. And this is still true. Now, a useful thing to do is to start using beta. In special relativity, beta is often used to represent v on c. So we can write v1 prime is equal to 2v over 1 plus beta squared. So let's just work out what this thing is in terms of beta. So we've got 1 over the square root of 1 minus, now this is 4v squared, over, we've got this c squared here, and then we've got this 1 plus beta squared. So this is equal to 1 over the square root of v squared on c squared, that's 4 beta squared, over 1 plus beta squared. Now this should have been squared, that's squared. This is 1 minus, so we're going to write this as 1 over the square root of 1 plus beta squared or squared. So we can write this as 1 plus 2 beta squared plus beta to the 4 minus 4 beta squared. And so this and this will cancel each other out and we'll end up with a negative there. So we can write this is equal to the square root of 1 plus beta squared squared over 1 minus beta squared squared. So that's equal to 1 plus beta squared over 1 minus beta squared. Now that's this term here. We've already got this term, so we can write P initial is equal to m v1 prime, so that's 2v over 1 plus beta squared times this thing, which is 1 plus beta squared over 1 minus beta squared. So these will cancel and we've got 2mv over 1 minus beta squared. Okay, let's clear this off now to get some space and then we can work out what the final momentum is. Okay, so what we're trying to do is now work out P final. Now, v2 prime, which will be the velocity in this equation here, is equal to v2x prime plus v2y prime. X prime we showed before was equal to v. So this is equal to v, and v2y prime will need to use this formula to work out what it is. So v2y prime is equal to vy. So this is referring to the velocity in the y direction in frame S. So this is v times the square root of 1 minus u squared on c squared. Now we said u was equal to minus v, so this is v squared on c squared, and then this is all over 1 minus u, which is minus v. Now vx, that's the x component of the velocity in frame s, which is 0. So this is 0 over c, so this is equal to v times the square root of 1 minus v squared on c squared. So this is equal to v root 1 minus v squared on c squared. So from Pythagoras, we can see that v2 prime is going to be equal to the square root of v squared plus v squared 1 minus v squared on c squared, which we were writing v on c as beta, so let's write this as minus beta squared. So this will be equal to v outside the square root of 1 plus 1 minus beta squared, which is v root 2 minus beta squared. Another way, we can write v is equal to c beta, so we can write this as c beta root 2 minus beta squared. Okay, so this is our v in this equation, and clearly the momentum in the y direction is going to cancel out and in the x direction is going to add together. So this v, we only need to consider the component in the x direction. So p final will equal 2m v2x dash, so just considering the x component, that's this part, over this thing, which is equal to the square root of 1 minus v2 squared, so that's c squared beta squared times 2 minus beta squared over c squared. Okay, so we've got 2m, now v2x dash turns out just to be v, and then we've got this over the square root of 1 minus 2 beta squared plus beta to the 4, which is equal to 2mv over the square root of 1 minus beta squared squared, which is equal to 2mv over this 2 over 1 minus beta squared. Now that's what we were hoping it was, because now P initial is equal to P final. So by defining the momentum this way, we've now solved our problem. So we've just seen in relativity that momentum is defined as mv over the square root of 1 minus v squared on c squared. So you may have seen written before m is equal to m naught over the square root of 1 minus v squared on c squared, implying that your mass changes as you go faster and faster. Now, this doesn't actually happen because mass is defined as the amount of matter within something, and the amount of matter is not changing. So I would urge you not to write this, even if you've seen this in high school. It's incorrect. Don't write it that way. Rather, it's the momentum which is changing, and the mass and this gamma term are separate parts of the momentum. Okay, now we're going to consider Newton's second law. We've said that all the laws of physics must be the same in all inertial reference frames. So we know Newton's law as F is equal to ma, which we can write as m dv dt. Now this isn't actually going to work in relativity. I'll leave it as an exercise to you, but practice showing that if this holds in frame S, then it does not necessarily hold in frame S prime. What we need to do to make Newton's second law work is, rather than defining the F as ma, if we define the force as dp dt, where P is this momentum, then this will hold in the relativistic case. Again, I'm going to leave that as an exercise for you to show that if this defines the force, then if that's true in frame S, it's also true in frame S prime. Now let's just show that this is correct in the non-relativistic limit. So in non-relativistic Well, we can write momentum in the non-relativistic case as mv. And in the non-relativistic case, the only thing which is varying is your velocity, not your mass. So we can pull mass out the front of this derivative as a constant. So this is dv dt. And this is indeed equal to Rma. So that agrees with our non-relativistic definition. So if we define force from now on as dp dt, then it agrees with everything we've done in relativity. Now let's just consider why we need this. Imagine a constant force acting on an object. Imagine a constant force. Now in the non-relativistic limit, this one, this would imply that dv dt was constant, and so our velocity is going to go to infinity as it's increasing constantly. And we've said in relativity that this can't happen, that there's a speed limit c in the universe, and so the velocity cannot become infinite. So what's the difference in relativity? So in relativity, we've got that the constant force would equal to dp dt, which should be equal to mv over square root of 1 minus v squared on c squared. Now as v gets big, this square root of 1 minus v squared on c squared goes to 0, and so we have to put in more force to overcome this term here as the velocity gets larger. So as v goes to infinity, need more force for same delta v, and it is in fact impossible to get your velocity up past the speed of light. Okay, so what we're going to consider finally is relativistic energy. Now, we know that if we do work on an object, we're adding energy to it and we're causing its kinetic energy to change. So we can say that the change in kinetic energy is equal to the work done on a particle or object. So the work done is equal to, if we're going from x1 to x2, it's f dot dx, which is equal to dp dt dx, using our definition for f. So now what we need to do is work out what dp dt is so that we can substitute it into this equation. So dp dt is equal to d dt of mv over the square root of 1 minus v squared on c squared. Now this m is our rest mass, it's not changing. The thing which is changing is the velocity. And so we're going to need to use differentiation by parts to find the derivative of this, but we can just pull the mass out the front. So this will be equal to m, and now we take the derivative of this part, so this is dv dt times 1 minus v squared on c squared to the minus 1/2. So we've kept this part constant this time. Now we'll take the derivative of this part and leave this part constant. So we've got this is plus mv d dt of 1 minus v squared on c squared to the minus 1/2. Okay, so let's do the next step. We've still got this term m dv dt, 1 minus v squared on c squared minus 1/2, plus mv dv. Now we need to take the derivative of this thing. Now you could do it by substitution, let u or something equal v squared on c squared and do the differentiation that way. That's how I'm going to do it, but I'm going to skip some of the steps. So if you're not too sure how to do it, just write out all the steps doing it by substitution. So when we do the substitution, we end up with the derivative of this thing, which is minus 2v over c squared. And then we need to dv dt, that's the derivative of this thing in here. And then we take the derivative of this whole lot, which is 1 minus v squared on c squared to the minus 3/2 times this, the minus 1/2. Okay, so now what we're going to do is pull common denominator out, which is m dv dt, and then we end up with 1 over the square root of 1 minus v squared on c squared, plus m dv dt is out the front. This minus and minus will cancel out, this half and this 2 will cancel out, and we end up with v squared over c squared times 1 over 1 minus v squared on c squared to the 3/2. Okay, so m dv dt, let's put this all over 1 minus v squared on c squared to the 3/2. So this first one becomes 1 minus v squared on c squared, and then we've got plus v squared on c squared. This and this cancel out, and so we end up with m over 1 minus v squared on c squared to the 3/2 dv dt. And what we can do now is substitute this dp dt into here. So we end up with the integral from x1 to x2 of m over 1 minus v squared over c squared to the 3/2 dv dt times dx. Okay, now I'm going to clear some space. So now that we've substituted that in, let's get rid of this. Okay, now we know that v is equal to dx dt. And if we're going to make this a function of v, then we need to change the x1 and the x2. At x1, we're going to assume that it's at rest. And at x2, it has some velocity u. So let's substitute this into here. So we've got our work, and our velocity changing from 0 up to u is m over 1 minus v squared on c squared to the 3/2. Now, dx dt, that's v, so this is v dv. Now, this is a standard integral. You can look it up. When we integrate it, we end up with mc squared. This c squared comes from down here over the square root of 1 minus v squared on c squared, and we evaluate that at u and at 0. So this is equal to mc squared over square root of 1 minus u squared on c squared minus mc squared over the square root of 1 minus 0. So this is equal to mc squared over the square root of 1 minus u squared on c squared minus mc squared. Now, this part here, this is the rest energy. So it's just due to the mass contained within the object. So if the object was at rest, it would have energy mc squared. So if we wanted, we could write this kinetic energy. This is W is equal to K, so the kinetic energy we can write as gamma minus 1 mc squared. Now what we're just going to do is consider the non-relativistic limit and make sure that this definition of kinetic energy agrees in the non-relativistic limit. Okay, so we've just said that the kinetic energy is given by mc squared over the square root of 1 minus, well, v squared or u squared, we'll put v squared, that's the final velocity, minus mc squared. So in the non-relativistic limit, v goes to 0, and our kinetic energy should be given by the normal thing, a half mv squared. So let's just check. We can write this as mc squared 1 minus v squared over c squared to the minus 1/2 minus mc squared. Now what we're going to need to do to get the low v limit is do a binomial expansion of this. Now a binomial expansion where this power is a fraction works in much the same way as if it wasn't a fraction. So we've got mc squared. Doing the binomial expansion, we end up with 1 minus v squared on c squared times this fraction, which is minus 1/2, and then there'll be other higher order terms, but they're much smaller as v is a lot less than c. This means v is a lot less than c. And then that's minus mc squared. So let's expand this bracket. We've got mc squared minus mv squared on 2, and that minus cancel, so we end up with plus that minus mc squared. So this is equal to a half mv squared, which is our non-relativistic definition of kinetic energy. So that's good. So total energy, E, is just equal to the kinetic energy plus the rest mass energy, mc squared. So you can see that this can be written as just this term, mc squared over the square root of 1 minus v squared on c squared. That's our total energy. Now, what we're going to end up by doing is just showing a useful expression. E squared is equal to p squared c squared plus mc squared all squared. You'll come across this again when you do quantum mechanics, so we're just going to prove it now. The easiest way to prove this expression is to substitute in for E and for P and show that the left-hand side is equal to the right-hand side. So remember, we've just said that the total energy E is equal to mc squared over the square root of 1 minus v squared on c squared, and we said that P was equal to mv over the square root of 1 minus v squared on c squared in the relativistic case. So let's just substitute in the right-hand side is equal to p squared c squared plus mc squared all squared. Substituting in for p, we've got m squared v squared times this c squared over 1 minus v squared on c squared plus m squared c to the 4. So putting it all over a common denominator, we've got 1 minus v squared on c squared, and we've got m squared v squared c squared plus, now we need to multiply this by this, so we've got m squared c to the 4 minus m squared v squared c to the 4 on c squared, so this is c squared. So this and this will cancel each other out, and we end up with mc squared over 1 minus v squared on c squared squared, and you can see that this is equal to E squared, which is equal to the left-hand side. So we've shown that now.
So one last question to do. We're told that we've got a micrometeorite with a certain mass travelling past the Earth with a certain speed, and we're asked what values will be measured for the energy and momentum of the particle by an observer in another system, S prime, moving relative to the Earth at 0.5 c in the same direction as the micrometeorite. And we're given a hint on how to do this. We're told to derive an expression for E prime, so that's the energy in the primed reference frame, and px prime, so the momentum in the primed frame, in terms of E and px, and then use this to answer the question. So let's start by deriving these expressions, and then we'll look back at the question. So as always, we've got two reference frames. We've got our unprimed reference frame, which in this case will be the reference frame of the Earth, but let's call it S. And then we've got a primed reference frame here. The primed reference frame S prime is moving at some speed u relative to the unprimed frame, and then we've got some object moving with some velocity v in the unprimed frame. In the primed frame, it's going to have some other velocity v prime. And so we know that in the original reference frame in S, the energy, the total energy, is given by mc squared over the square root of 1 minus v squared on c squared. And we know that px is equal to mvx over the square root of 1 minus v squared on c squared. Py is equal to mvy over the square root of 1 minus v squared on c squared, and pz is equal to mvz over the square root of 1 minus v squared on c squared. Now in S prime, we're going to have slightly different expressions, but very similar. E prime is going to be equal to mc squared, doesn't change, and then in this expression we'll need to replace this v squared with a v prime squared. So this is over the square root of 1 minus v prime squared on c squared. In a little bit, we'll look at how we can simplify this further once we calculate this bottom term. But let's just list down the other expressions. So we've got px prime is equal to mvx prime over the square root of 1 minus v prime squared on c squared. We've got py prime is equal to mvy over prime over the square root of 1 minus v prime squared on c squared, and pz prime is equal to mvz prime over the square root of 1 minus v prime squared on c squared. Okay, so you can see that to simplify these expressions, we're going to have to work out this term on the denominator, the 1 minus v prime squared on c squared. So to do this, let's start by coming up with an expression for v prime squared. We know that v prime squared is equal to vx prime squared plus vy prime squared plus vz prime squared. Pythagoras' theorem works in all reference frames. So now what we can do is substitute in our expressions for these things here, because previously we've calculated, well, we've shown what vx prime is in terms of v. And so all of these terms actually have a common denominator. The common denominator is 1 minus u vx on c squared. And so we know that vx prime is equal to vx minus u over 1 minus u vx on c squared. So this should be squared when we square it. And so this is equal to vx minus u squared. And then the vy prime term, this is equal to vy prime is equal to vy times 1 minus u squared on c squared, square root of that, over this. So we can put that as vy squared 1 minus u squared on c squared, and then z and y are exactly symmetric. So we've got the plus vz squared 1 minus u squared on c squared. So we've now got an expression for vy prime squared. Okay, so to substitute this into here, we're going to need an expression for 1 minus v prime squared over c squared. So we need to do 1 minus this and then divide this thing by c squared. Let's still give it a common denominator, so let's still put this 1 minus u vx on c squared term down the bottom, and then to get this 1 we'll have 1 minus u vx on c squared squared, and then we need to minus this v primed squared and divide it by c squared in the process. So let's write this as vx on c minus u on c squared, so just dividing that by c squared and putting the c's in the brackets, plus vy squared on c squared, 1 minus u squared on c squared. Sorry, that's a minus because we're subtracting it here. And then this is minus vz squared on c squared, 1 minus u squared on c squared. Okay, now to simplify this further, we need to expand these brackets. So let's have a go at expanding the brackets. We've still got 1 minus u vx on c squared squared in the denominator. So expanding this, we've got 1 minus 2u vx on c squared plus u squared vx squared on c squared, sorry, c to the 4, because we're squaring it, minus vx squared on c squared plus 2vx u on c squared, and this term will cancel this term, and then we've got minus u squared on c squared. And then we've got the minus vy squared on c squared, 1 minus u squared on c squared, minus vz squared on c squared, 1 minus u squared on c squared. Now what you can see is nice is this term and this term have a common term of 1 minus u squared on c squared. And if we combine this vx with this vx term, that's going to have the same common term as well. and then we'll be left with 1 minus u squared on c squared. So that has a factor of 1. So we can actually pull 1 minus u squared on c squared out the front as a common denominator. So there's a little bit of room here. Let's just try and squeeze it in here. We've got 1 minus u squared on c squared as a common factor. We've still got the common denominator, 1 minus u vx. Sorry, that's vx on c squared squared. And then we've got this common factor. Sorry about the slight mess here. We'll go up here later. And so we've got, in this case, this 1 minus u squared on c squared is a factor of 1. And then in this case, we had to pull the vx squared on c squared out the front. So that's minus vx squared on c squared minus vy squared on c squared minus vz squared on c squared. And then minus vx squared minus vy squared minus vz squared. Well, that's just minus v squared. So we've got 1 minus u squared on c squared, 1 minus v squared on c squared, over 1 minus u vx on c squared squared, and that's what this thing is. So we can see that 1 over the square root of 1 minus v prime squared on c squared is just going to be the square root of this inverted. So we will have 1 minus u vx on c squared over the square root of 1 minus u squared on c squared, square root of 1 minus v squared on c squared. And previously we were saying that 1 over the square root of 1 minus u squared on c squared is equal to gamma. So that'll make it a bit faster to write everything out. So now we've got the expression for this part, and we've just got the mc squared here. So now we can substitute this in here to simplify this expression here. So we've still got the mc squared on the top. Now we've got the gamma from the 1 on u squared minus c squared, so let's put that out the front. And then we've got 1 minus u vx on c squared over the square root of 1 minus v squared on c squared. And so mc squared over the square root of v squared on c squared, this first term, that's just e. That's what this thing was. So we can write this as gamma, and we've got an e. And then the second term is on the square root of 1 minus v squared on c squared still. We've got an m, we've got a vx. We've also, so you can see the m and vx on 1 minus v squared on c squared, that's the px. And then we've got a c squared divided by a c squared, which will give us 1. So there's just a u left there. So this is going to be minus u px. So we've now come up with an expression for e prime in terms of e. Now we're going to want to simplify this one. Okay, so substituting into this, we know we've got the m, now vx prime, we know that that is equal to vx minus u over 1 minus u vx on c squared. And then we've got to substitute in this, which is over here. So this is equal to the gamma, and then it's the 1 minus u vx on c squared over, we've got the square root of 1 minus v squared on c squared. So nicely this term and this term cancel out, and so we have gamma m vx, which is on 1 minus v squared on c squared, which you can just see is equal to gamma times px, and then we've got the minus u minus mu over the square root of 1 minus v squared on c squared. This term's not quite so nice, but what we can see is that e is equal to mc squared over the square root of 1 minus v squared on c squared. So the difference here is the c squared and the u. So we can actually write this part here as e times u, and then we need to divide by c squared to get rid of this c squared term here. So let's replace this with eu on c squared. Now, as the reference frames are moving relative to each other in the x direction, so u is in the x direction, we would expect py and py prime to be the same and pz and pz prime to be the same. We can just substitute in. We've got the m. The vy prime we know is equal to vy times the square root of 1 minus u squared on c squared over 1 minus u vx on c squared. And then we've got our gamma times 1 minus u vx on c squared, which will cancel with this one. And then we've still got that root 1 minus v squared on c squared. Now this gamma and this 1 minus u squared on c squared are going to cancel each other out, and we're left with mvy over the square root of 1 minus v squared on c squared, which you can see up here is the py. And so this has not been transformed, and you can see that because pz and py are exactly symmetric, this is going to be equal to pz. So we've now come up with our expressions. We can now answer this question, but let's just write the expressions up here and then we can clear the screen to answer our actual question. So we've got E prime is equal to gamma E minus UPX, and we've got PX prime is equal to PX, well, gamma PX minus EU on C squared. Okay, so let's clear some space now. Okay, so let's go back to our original question and carefully define everything. So let's draw the Earth's reference frame. Here's the Earth's reference frame. This is S, which is the Earth, and it has some micrometeorite moving with some speed v is equal to 0.01 c. And then we've got a second reference frame, our S primed frame. Let's draw it here, which is moving in this direction parallel to the micrometeorite with some speed u is equal to 0.5 c. And we're told that the mass of the micrometeorite in the Earth's reference frame is equal to 10 to the minus 9 kilograms, and we're now asked to calculate E prime and PX prime. Okay, so what we're going to need to do is substitute in here. So we're just going to need to work out what each of these terms is. So let's start with gamma. Gamma is equal to 1 over the square root of 1 minus u squared on c squared. And so this is equal to 1 over the square root. You can see u here is equal to 0.5 c. So this is 1 minus 0.5 squared c squared on c squared. So those cancel out, giving us 1. And so this is 1 over the square root of 0.75. And solving that on the calculator, we end up with this being approximately equal to 1.1547. Okay, next we're going to have to work out what E is. E is equal to mc squared over the square root of 1 minus v squared on c squared. And so we've got 10 to the minus 9 c squared over the square root of, now v in this case is 0.01, so minus 0.01 squared, c squared on c squared. Those will cancel, and so we end up with 10 to the minus 9 c squared over the square root of 0.9999. So solving this one on the calculator, we get 1.00005 times 10 to the minus 9 c squared joules. Now calculating px. Px is equal to mvx over the square root of 1 minus v squared on c squared. Now Vx is equal to V because the micrometeorite is moving in the x direction. So we can write this as 10 to the minus 9 times Vx, which is V, 0.01c, over, we've got the same denominator here, so 0.9999. So solving that one on the calculator, we get 1.00005 times 10 to the minus 11 c squared. That'll be kilograms meters per second. Okay, so now we've calculated everything, so we can just combine it. So E prime is going to be equal to gamma, so that's 1.1547 times E, which is 1.00005 times 10 to the minus 9 c squared, minus U, which is 0.5 c times px, which is 1.00005 times 10 to the minus 11. That shouldn't be a c squared, it should just be a c. Okay, so solving this one on the calculator, we end up with E prime is equal to 1.14898 times 10 to the minus 9 c squared joules. Now we can do a similar thing for px. So px prime is equal to, in this case, gamma, which is the 1.1547, times px, which is 1.00005 times 10 to the minus 9 c, times E, which is 1.00005 times 10 to the minus 9 c squared, times U, which is 0.5 c, all over c squared. So those will cancel. And so solving this one on the calculator, we end up with minus 5.66 times 10 to the minus 10 c kilogram meters per second. We would expect to get a negative answer because if we're traveling faster than this micrometeorite, it's going to look like the micrometeorite is going in the negative direction. So these seem reasonable. Let's just do one final check. Let's check that E squared is equal to P squared C squared plus M squared C to the 4 in this case. In this case, the left-hand side is equal to E squared. So that's equal to this 1.4898 times 10 to the minus 9 c squared squared. And so calculating that, we get 1.320 times 10 to the minus 18 c to the 4. And the right-hand side, we're going to need to do p squared, so minus 5.66 times 10 to the minus 10 squared times c to the 4th, because it's this c squared times c squared, which will give us the power of 4, and then plus 10 to the 9 squared, so that's 10 to the minus 18 times c to the 4. So solving that one on the calculator, we get 1.320 times 10 to the minus 18 c to the 4. So you can see there is agreement here. So it does look like we've derived these expressions correctly and answered that question.